Good morning and good afternoon, everybody, and welcome to our webinar. We will start in about 2 minutes. So while people are joining, we'll just play a little video for you, and we will start the countdown.
IGS is in the business of protecting mission-critical surfaces. One of the ways that we do that is through the IGS Technology Solutions Laboratory. So here we do a lot of work on developing the technologies that will give that protection. What's really, really valuable to us at the end of the day is whether we can get to our joint mission, and that is to make sure that everything is running the way it should. This is the way IGS operates, by making sure that we understand our customers' problems right from the get-go, that we develop the technologies that are going to give us the solutions and the performance that we need down the line. And we only do that effectively when we can engage with you to make sure that we're operating side by side so that we achieve our joint mission, which is the reliable, safe operation of your equipment.
So hello, everybody, and thank you for joining us for our webinar on how to stop acid gas corrosion in amine systems. My name is Marina Silva, and I will briefly go through the setup and introduce our speaker. So our speaker today is Colin Bateman. Colin has over 20 years experience in solving corrosion and erosion challenges in processing equipment, including refineries and petrochemical plants, among others. He is very well versed in non-metallic and metallic coatings, and today he'll be sharing his experience and expertise in protecting amine systems from corrosion. This webinar is live. We will be sharing slides, video, and audio.
Okay. Thank you very much, Marina, for the introduction. So first of all, good morning, good afternoon, good evening, everybody. And thank you very much for joining us. We very much appreciate you taking some time out to listen to our webinar today, particularly given the unprecedented times that we're in with the COVID-19 pandemic. So I hope that from today's webinar, you'll glean some useful information that will help you manage some of the challenges that you're facing in your processing and operating environments. And the fact that so many people are joining tells me that this is a very live subject. It's a real subject that is affecting people in operating plants, and that the management of amine systems and their operation is a challenge for everyone. Corrosion can appear in many forms and many kinds, and we'll talk about that in the presentation, but clearly amine systems pose some individual challenges that can be addressed in different ways. What I would like you to take away from today is the fact that the utilization of an effective corrosion barrier can be a new tool or a tool in your toolbox to help you create a robust preventative maintenance strategy to give you more reliability from your equipment and to remove hopefully some of the headaches that you face in regards to the operation. As Marina said, it's interactive. Please do pose questions in the chat or in the questions bar on the right, and we'll endeavor to answer all of those at the end of the presentation. And if you do lose or drop out for any reason, then we are recording the webinar, and we'll make that recording available to you afterwards so you can watch it and listen to it in your own time. So without further ado, let's begin. So just with the presentation itself, I just want to start with a brief introduction. I want to talk about material selection when we're looking at the operating conditions inside an amine system. We need to think carefully about what type of materials are most applicable to be resistant to that environment. I then want to have a think about how we get those materials installed, particularly if we're looking at an in-field or in-situ application. during a shutdown or turnaround, brownfield opportunity, what methods are there to do that, and which methods are going to be most cost effective, I'd say, and beneficial to you as the client. We'll then look at some case histories. So IGS, we've been doing Amine column applications since around 2000, 2001. We have some long case histories that we'd like to share with you that demonstrate the long-term performance of these corrosion barriers in this environment. And finally, we'll just conclude with some closing comments. So Amine units, I think we're all aware that they play a vital role in our processes today. We understand that we have to remove the contaminants from our feed, like your H2S and your CO2, and that's required for our downstream processes, and also as we're pushed to create even lower sulfur fuels, cleaner fuels as part of our production. And an Amine system is integral to the operation of our whole process unit. So if we have an unplanned shutdown, if the Amine system stops operating, then it can have a serious knock-on effect to the total processing capacity of the plant and also on the revenue. And depending upon the size of the facility, this can lead to costs of hundreds of thousands a day, obviously depending upon what you're producing. Amine systems, we know, are a big challenge, and we understand that they create issues from an operational point of view. IGS, we're very fortunate to go to a recent conference and witness a presentation by a company who specialize in the operation of Amine systems and how to manage those plants from an operating perspective. What this company is called is Amine Experts International. I believe Philip is also on this call. And they did an in-depth study looking at 400 cases of Amine system failure to understand what the root cause was and to provide some insight of how you can address those root causes through different mechanisms, some to do with operational parameters, some to do with material parameters. And what was very clear was that corrosion was a major factor when we looked at Amine system failures. And despite the fact that a perfectly designed system with the right materials incorporated shouldn't corrode from new, or if operating under design parameters, that is clearly very difficult to maintain in a real life situation. And Amine systems in particular have many different areas inside them that create challenging environments from a corrosion perspective. So as well as reviewing the different cases, they also had a look at where these were located in an Amine system. And what we see is a fairly general overview here of the locations where the corrosion challenges were taking place. And what we can see is there's different areas of the plant that face different issues. So depending upon whether you have a CO2 stripper, an H2S stripper, CO2 stripper, your oxide layer or your passive layer on the surface of the steel is going to be iron carbonate. That's a relatively fragile material. So if you have high velocities or medium velocities, you have any type of entrainment or impingement on the surface, you'll remove that oxide layer, creating an erosion corrosion cycle. And as you remove more of the oxide layer, if you don't have a good filtration system, then you further accelerate that process. H2S poses other challenges. H2S obviously is a acid gas. H2S can lead to problems such as cracking, sulfide stress cracking, acid attack. And in areas where you have low velocities, you can have deposits. Under those deposits, you can then create dissimilar environments, low oxygen contents, and have similar to galvanic corrosion taking place. So all of these areas in the Amine systems have risks, and those risks can lead to corrosion. The majority of the corrosion types that we come across principally is pitting corrosion for various reasons that we just talked about in terms of those erosion corrosion mechanisms. But also we do come across cracking, particularly in situations where clients have had to do some remedial repairs, some mechanical work, some internal welding that's then led to changes in the substrate or metallurgy, changes in hardness. And those are key things we need to think about, or parameters we need to think about with material selection. We need to think about, do we have the right material hardness, and do we have the right material selection from an alloy perspective to be resistant to the environment? So with thermal spray itself, I would imagine most of you have some experience of thermal spray, but that's likely to be with a system like thermal spray aluminium, which is used to externally protect equipment from environmental corrosion. Now, TSA can be used in situations where it's permeable. You have the aluminium in there as a sacrificial material to prevent the corrosion of the steel substrate. Where IGS are working, we're working inside the units and we're applying a higher nobility alloy. So we have to eliminate any permeability. Otherwise, even if the alloy is resistant, if it's permeated, then the substrate will corrode underneath and pop off your thermal spray cladding. So IGS, we looked at the processes we had available, a standard or a conventional twin wire arc spray process. So here you've got your two wires coming into the gun. You've got your arcing point outside the gun, and you've got your gas flow hitting that arcing point and then projecting those particulates onto the surface. And what we found was the particles were relatively large. They were relatively poorly configured in terms of the microstructure, and also that they had a large amount of porosity. And that meant that there was typically an easy pathway for the corrosive species to get to the substrate to cause breakdown. So the way we addressed this was to redesign the gun itself. So we brought the arcing point inside the gun, and we created a supersonic high velocity gas stream in that location. And what that meant is we strip off smaller particulates, and more importantly, that they hit the surface with greater energy. So when they hit the surface, they flatten, or pancake, as we like to call it, and create this extremely dense interconnected structure. So as long as we've built sufficient thickness and we have enough layers of the particles on the surface, then we eliminate any potential pathway through to the substrate. So if we have the right alloy selection and we use a high velocity process, we can create this inert barrier. The other challenge with thermal spray is it's an aggressive process for the alloy itself. So we're melting a material and then we're projecting it through ambient conditions to the substrate. So it's going to react with the oxygen in the atmosphere. Now we need to ensure that the alloy is sufficiently modified so that we have the right components once it's applied onto the surface. And we also need to prevent the oxides creating a weakness within the inherent applied system. So with IGS, we don't use conventional alloys. We've developed bespoke alloys where we're ensuring that the alloy constituents are consistent once it's been applied onto the surface. So elements such as chromium, which readily oxidize in the air, we have to manage that element to make sure that once it's applied, we still have sufficient levels of chromium to give us that same resistance to pitting that we need to perform. IGS are a thermal spray company. We're an on-site thermal spray company. That's our business. And these developments, these material developments, have come at some cost to IGS because we've experienced the failures of these systems when they're not designed and they're not applied correctly. So we've used low velocity, we've used standard off-the-shelf conventional alloys, we've used micro-cracking materials, which are very good for high erosion environments or abrasion environments. You can have a very hard material that micro-cracks, but then provides a very good sacrificial barrier to erosion. But if you're looking at corrosion, those microcracks then provide a pathway to the substrate. We've used HVOF systems, so high velocity oxy-fuel, and these create a very dense microstructure. But if you're applying them in the field, it's very difficult to control the parameters. So if you're doing a shop work with a controlled environment, robotic application, perfect. If you're in the field working in a vessel, it's almost impossible to control the parameters. And what that means, because it's a highly stressed material, is you can get macro cracking and failure and disbondment. So IGS have worked with all of these materials and experienced the difficulties of managing them in the field. And that's what led us to develop what we're using since around about 2000 and today, which is a high velocity process where we utilize a bespoke alloy to reduce the oxide content, reduce the internal stress, and make it applicable and robust to applications in the field. So this is the way that we get a corrosion-resistant alloy, a high nobility alloy, onto the internal surface of your equipment in order to resist the corrosive environment. And we provide this long-term protection. So what I would like to now is just talk through a few examples. I apologize for the photograph here. It was taken at night time, but I assure you this is the Amine AGR absorber column where we did the application. This was a client who we started working with around about 2010, and we started doing some inspections with them. And when it came to their turnaround in 2011, they understood that they were going to have some challenges with pitting corrosion in these absorber columns. Like many of these columns, the original design had a clad section in the top of the column where it had 316 stainless steel incorporated. The problems they had was below the cladding. They were having corrosion creep coming down the column, and they were seeing some relatively aggressive pitting taking place. So with IGS, we discussed with the client how to install a corrosion-resistant barrier using the high-velocity thermal spray process. And we did this using our standard operating procedures. So at IGS, we're a company that does a turnkey service. So what we do is we work with you to develop a solution. We look at the situation you have, the environment. If necessary, we can do some testing in-house to ensure that the alloys we're using are appropriate for that application. We'll then bring our equipment and materials to site, which are strategically located throughout the world. We bring in our personnel and do the application. That includes doing the surface preparation to ensure that we have the right cleanliness and profile of the surface and the application of the thermal spray. So from the client's perspective, it's a turnkey approach. And then more importantly, we want to be with the client throughout the lifetime of that system. So we'll do follow-up inspections with the client, and we'll go through the client any requirements that there might be for expansion or changes to the system that they're using. So with this client in 2011, we applied the IGS 5420 system, which is the standard system we're using, as I said before, a Hastelloy-based alloy for these environments. We went back in 2016 after 5 years in service, and then we were back again just in February this year in 2020. We did the inspections, and we found, as we expected, that there was no degradation of the internal cladding. When we do an inspection, what we can do is we can measure the thickness of the thermal spray cladding on top of the steel. So we have thickness maps from when we do the original application, and then we can compare those to thickness maps we make during an inspection. Typically in a corrosive environment, you don't see any reduction in the thickness. If you do have erosion taking place, obviously that's a mechanical process. And if you do remove some of the thickness, then that can be reapplied locally as required during the shutdown. So it's a system that can be repaired in situ. There's no issues with doing localized repairs if that's required after it's been in service. In this situation, it was almost exclusively an corrosive attack. I'll get that right. So there was no pitting, no requirement to do any work. So for this client, we've been in operation now for 9 years in this unit. We prevented any further pitting taking place. They're quite happy to button up the unit and carry on. It gives them an opportunity to think about extending the time between maintenance interventions in these units. And we'll talk about that a little bit later as a key benefit that we can offer. This is a slightly different situation. This was an MDEA column in an MGL plant. In this column, it was a discovery scope, so there was no planned activities to take place. During the shutdown, the client found he had very aggressive, localized corrosive attack and washing out of material. And it was because upstream of the unit, one of their reboilers was leaking, and they were getting an aqueous environment in an area of the column that shouldn't have been there. And effectively, this was creating an acid that was rapidly eating away the substrate. So for the client, this was a critical situation. The first thing they had to do was a fitness for service inspection to make sure the column was still fit for service, safe to operate. It passed, but what it did demonstrate was that in many locations around this middle section of the column, they'd lost the majority of their corrosion allowance and were right on the minimum in terms of their remaining steel. So they had to install a system that was going to stop any further corrosion and freeze the condition of the metal. They looked at doing a weld overlay service in this application area. What that would mean is having to stabilize the tower, having a crane, loosening obviously the flanges, the joints on the tower while they did the work, and also post-weld heat treatment. So that was going to potentially extend their shutdown by 3 to 4 weeks, which was unacceptable. So the IGS thermal spray solution was much more attractive to them from the perspective of keeping it within their original turnaround schedules. You can see from the pictures there some of the aggressive nature of the acid washout from the carbonic acid. With the IGS application, as long as we can see the surface, as long as there's no shadowing of the spray, we can apply the thermal spray system. So if we have deep pitting or deep channeling, as in this case, we'll use a mechanical method like a grinder to open up those channels, open up those pits, being very careful not to remove any more of the substrate material. Once it's opened up, we can then do the surface preparation and apply the thermal spray system. The client was looking for initially a 4-year solution. After the application of the thermal spray, they closely monitored the column itself, because these areas where they had low thickness, where they were close to being at their minimum thickness, clearly they had to make sure they didn't lose any more material. Otherwise, they would lose the fitness for service and the license to operate that column. What the thermal spray application allowed them to do was then to plan replacement. So around about 2016, they'd done a debottlenecking exercise previously, and they planned to replace the single column with 2 larger Amine columns to improve their process versatility and their flow. What this graph shows is their ongoing inspection. And on this particular column, in the different areas where they had the minimum wall thickness. And as you can see, we were able to prevent the column losing any more of its shell, any more of its pressure boundary, allowing them to operate for the next 6 years. Originally, this column was part of the process and did not have any bypass. So when this column was down, the train was down. So it was absolutely critical for them to get it back up and running as quick as possible. And I think what this demonstrates is our capability to be very reactive to problems. If you do have a situation during a shutdown, even if you haven't contacted us before, please pick up the phone and speak to us, and we can probably help. The last example I want to talk about is not, strictly speaking, an Amine column, I understand, but I wanted to talk about also cracking. This is a phenomenon we see particularly in older vessels. This vessel was built in the 1970s and had no issues until the client replaced the internal supports for the trays. And when they welded in the new tray supports, they didn't do the post-weld heat treatment correctly. So they created these areas of material hardness, and those areas became susceptible to cracking. And what they started to see over time was an increase in the amount of cracks, as you can see from the data on the left. And this suddenly jumped. In 2013, they decided they had to do something about this because they were seeing corrosive activity that was creating the atomic hydrogen that was then increasing the amount of these cracks and potentially leading to big challenges in terms of stepwise cracking and blistering. So the client looked at the different opportunities available to them to protect the column. They needed a corrosion-resistant barrier, and they needed to install a corrosion-resistant alloy. Welding was a possible solution to this, but what it would have meant for them is to take the column out of situ, to lay it horizontally on the ground so they could do the stepwise post-weld heat treatment, which was obviously going to add a significant amount of time to doing the work. Once they were confident that IGS could put an alloy on the surface that would be resistant to the environment, and they were confident with our process in creating an impermeable barrier, we moved ahead with the application of the IGS system. So this is a large column. Internally is around about 635 square meters. And what we can do at IGS is we can scale up our services on site dependent upon the amount of work that we have. So in a column like this, when it's scaffolded, we can have applicators working on multiple levels in order to reduce the total time required to install the thermal spray barrier. So we did the full application in 2013. Prior to us doing the thermal spray application, which is the corrosion barrier, the client first of all had to ensure that all the cracks that were present had been terminated. So he did his mechanical work on any cracks that were deemed to be at risk, grinding them out and doing re-welding and then localized heat treatment. Once that was complete, we could then come in and do the surface preparation and the application of the thermal spray system. So the original project, it was 2013. 1 year later, the client wanted to go in and have a quick look just to check that everything was okay, to make sure that they weren't seeing any more of the same phenomena. We did that, everything was fine, bottled it up, and then we had a full maintenance shutdown, a full plant shutdown in 2018 after 5 years of service. And what they found was that there was no breakdown of the thermal spray system, as we would expect. The alloy itself is resistant to the environment, and so long as you have a sufficient application process so that you create an impermeable barrier, and that alloy is going to sit on the surface quite happily and stop any further corrosion of the substrate. So after 5 years, we didn't need to do any repairs. The client put the column back into service. And what I want this to demonstrate is that even if you have surface cracking, as long as that cracking isn't going beyond your corrosion allowance, as long as that cracking can be mechanically addressed and it's being driven by a corrosive process, so it's not mechanically driven, it's driven by corrosion, we can stop that. And we've many examples where we're applying this system in order to address localized cracking issues. For example, on weld seams or in areas where you have heat-affected zones. So with Amine systems, we have a lot of experience. As I say, the first Amine columns we did at IGS was 2000, 2001. And that particular column is still in service today. This table on the right just shows some of the scope in terms of the different types of Amine systems we're being applied in. These are just applications we've done in one particular region in the Middle East. But it just gives you an idea of the type of scope that we have and the sort of applications that we're doing. You can see there's quite a variance in the coverage areas that we're doing in the different columns, and that's often dependent upon how they're run and, as you can imagine, the sort of challenges that they're experiencing. We can be very bespoke in terms of how we design with the client the corrosion barrier system they want to incorporate. We can address just the specific areas where they have the challenges and utilize the system as cost effectively as possible for them. Because we understand, people don't have limitless budgets. We have to manage what we can do within that budget to address the challenges that they have. When we think about the long-term performance, IGS, I think, has proven that with this process, we can install a corrosion barrier that survives over the long term. And we go through 1, 2, 3 inspection cycles. And what we like to think about is the total value to the client of that type of service and the cost of ownership of that corrosion barrier rather than the cost of purchase. So what we can eliminate, if you like, repeat reapplication. We can eliminate mechanical repairs. We can eliminate problems with replacing that corrosion barrier, and also what those issues might do to a shutdown schedule. And over time, that creates significant value for clients, which is why I think with IGS, we have long-term relationships with facilities, with clients, once they perceive the true value that we can bring over time with these types of systems. What we haven't incorporated in here is things like lost production revenue. If you do have to extend a shutdown, which is typically the biggest opportunity cost, or if the corrosion goes beyond your allowances, then what that means in terms of a replacement of a vessel. So to sum up, really, if we want to look at the benefits that this type of solution can bring, one of the key things is eliminating any further corrosion taking place, having the application of a suitable corrosion-resistant alloy internally to stop it. And what you can see from the applications that we've done is that we can achieve that over the long term. And we work in environments that are extremely aggressive. So we work in locations where they have very high levels of H2S, CO2, they have very aggressive processes, and we're able to install alloys into these units that are resistant to these environments. Once we can demonstrate that capability and the client develops some confidence in the long-term solution, they can start looking at changing some of their maintenance procedures. So perhaps they can look at extending the time between intervention into these columns. So for example, move from a 3 to a 4 to a 5 year shutdown schedule. And if you look at that over a 15 or 20 year period, you're potentially removing 2 or 3 shutdowns over that period, which can have significant benefits from a revenue perspective. In addition to shutdowns and internal inspection, what IGS can do is we can do an online condition assessment of your internal thermal spray cladding. So we can use inspection technologies while the piece of equipment is in operation to take measurements from the outside and identify that the internal cladding is still in situ and that it's still doing its job of protecting the substrate from corrosion. And we can do that condition assessment online. And we've been doing that successfully for clients for a number of years. And that adds additional confidence when they're looking, for example, to extend time between interventions or shutdowns. What this means for you is a reduced maintenance cost. I mean, clearly, if you know you have a reliable corrosion barrier, you don't have to worry about internal pitting. You don't have to think about the problems you might have with having to do localized weld buildup, with having to do mechanical repairs during a shutdown. And it should help to reduce those unexpected or discovery problems that you'll find in a typical TAR. And what that helps with is reducing your shutdown schedules. So if you have a reliable and robust barrier, you know that in your shutdown, you're not going to be needing to do so much work in these units. You can reduce that schedule and concentrate on other areas in the plant that really require your attention. Hopefully meaning that you can be more efficient and again, knock some days off those turnaround schedules. So to sum up, what I hope you've seen from the presentation is that we have a proven technology that is robust. It can apply a high nobility alloy internally in these vessels in order to stop the corrosion. So we can reduce your downtime over the lifetime of the solution. We deliver a high value and a high return on investment. And we can look at a permanent solution in the sense that it's a corrosion barrier which is inert to the environment. So as long as it's been applied in the correct way, you're not going to get a breakdown of that surface barrier. IGS, very briefly, as I said before, we're able to be reactive. We are a global company. We have our operations facilities located strategically around the world. So in North America, in Europe, in Africa, in the Middle East, in the Caspian region, and in Asia. So if you have a facility wherever you are in the world, I think we can be quickly reactive to any problems you have to support you if required during a shutdown. So we're obviously very keen to hear of any challenges that you have that we may be able to help you with. So I hope that's given you a brief overview of IGS, of our core technology, which is thermal spray, and also an idea of our capabilities in order to support you as clients. So, Marina, we have some questions.
Yes, Colin, we have quite a lot of questions, and thank you very much for this amazing presentation. I'm sure everybody will agree with that. So we'll go through some questions in the chat first, and then we'll move on to the questions tab. So the first question we have is from Jinesh, a question about TSA that's been used and accepted for external corrosion under insulation applications. Is it endorsed for internal applications?
Typically, TSA is applied as a sacrificial material. So the aluminium in there is designed to be sacrificial to prevent the substrate from corroding. So what that means is that permeability is not considered to be a critical part of a TSA application. So if the internal environment is suitable for TSA, in other words, if the internal environment is benign in the sense that the TSA is not going to be attacked, then it could potentially be looked at as a solution. But in the majority of systems we're working in particular amine systems, TSA is not a suitable alloy to use, or aluminium is not a suitable alloy to use to provide long-term protection.
Thank you, Colin. A question from Sabari about the minimum thickness of HVTS, and also does it add strength to the base material?
We chose that thickness based upon a lot of corrosion testing that we did to ensure that we eliminated any potential pathways to the substrate. It's a corrosion barrier, and we are not adding any thickness to the substrate from a mechanical strength perspective. So you cannot include the thickness of the thermal spray in any calculations for pressure boundary. So no, it does not add strength to the substrate. It is just a corrosion barrier.
Thank you, Colin. And follow-up question, will external UT check be able to see the base metal HVTS alloy interface, or is it a metallurgical bond and therefore provides a total thickness?
No, what we basically get is two signals coming back. So we can see the substrate, obviously the base alloy thickness, and then we do get a signal coming back from the thermal spray. So in order to get that signal, the thermal spray has to still be tightly bonded to the substrate. So the first thing we can see immediately is the thermal spray barrier still there? Because if we're getting that second signal, we know that it's still tightly bonded. Because we apply a very dense alloy, we know, or a dense microstructure, I should say, we know the relative speed of sound through the thermal spray system. So we can get a feeling for the integrity. The key thing is to understand that it's still there. The way that the thermal spray system fails, if it fails, is typically being popped off the substrate. So the metal itself is inert to the environment. It's not going to corrode. So it's not going to dissolve or anything like that. The failure mechanisms typically, if you have permeation, the substrate corrodes underneath and pops it off. So what we're looking for to do an assessment of its integrity is to make sure that it's still tightly bonded to the substrate. So that signal tells us that that's the case. And in some cases, if we take accurate baseline measurements, we can also, within a certain tolerance, measure the thickness of the thermal spray as well.
Great answer, and I hope that answers your question, Sabari. So next question we will take from Anjanaya, also about our online inspection. What type of UT probes are being used for online condition monitoring of HVTS? Because of regenerator temperature is about 110 degrees Celsius.
Yeah, so we obviously need to have the right coupling gel so that we can make a good contact with the metal surface. So we need to use the right type of gel for the temperatures that we're operating in. In terms of the specific UT probes, I think that's information we could share with you on an offline conversation, because we do have some information on our external testing. But also it's something that IGS are doing. So we're quite happy to share that with you given the opportunity. But I don't think going into the detail of the equipment is appropriate for this format.
Mm-hmm. Thank you, Colin. We'll go to the questions tab now with our first question from Arjun. This AGR amine absorber case study, Colin, you were talking about, can you explain why there was corrosion there? And was this due to the difference in operating conditions?
I think it's the pitting corrosion, I think, was due to obviously a localized attack of the substrate. I think it's to do with process control. A lot of these amine columns, it's not, as I said at the beginning, the original design is fit for purpose. So if they were operating the column to all the correct parameters, then they wouldn't have experienced the corrosion or the pitting that they saw. But I think we all know that operating in the real world is more challenging, keeping it to the design conditions. And so I think it's the pitting corrosion was due to the substrate attack in that area below where the original cladding was put in place. Obviously, original cladding is put there to try and protect the most susceptible area, but due to their process control, that area, started to creep down the column, or they saw it in different locations in the column. We can send some specific feedback on the mechanisms that they saw in that column if required, or if you'd like some more information.
Thank you for that, Colin. We also will have a survey at the end of this webinar. So if there's any questions, follow-up questions or follow-up information anybody would like to receive, we welcome you to type that into the survey so that we can follow up. Next question we'll take is from Omar. Could you use this technique for flush chambers in the desalination plant type MSF?
So in terms of application, it's a physical application. So we need to get somebody in there to do the surface preparation and to do the application of the high velocity thermal spray. Normally that's the limiting factor we have in terms of what pieces of equipment we can apply this to. So for example, we can't do pipelines, we can't do small diameter vessels or columns. So typically when it gets down below 1.5 meters, 1.25 meters internal diameter, it gets very difficult to do the application. So without having a sort of general arrangement drawing of your equipment, it's hard to say if it's applicable or not. From the perspective of developing an alloy or having a corrosion barrier material, yes, I would say we would certainly be able to do that. I think what's more challenging is, can we actually apply that alloy in your piece of equipment? So we'd need to have a look at a drawing to understand what the access is like.
Thank you, Colin. Next question from Michael about surface preparation. Is the same aggressive surface prep required when spraying on an existing thinned coating as opposed to an original metal surface?
Yes, I would say we're still looking to generate the same profile. So because the thermal spray process is effectively a dry process, so it's not like a liquid where it's going to flow. So if you have, if you create the right profile originally, when you apply your thermal spray on top, that thermal spray will mimic the profile underneath. So generally, it has a good roughness on the surface. When we have to do localized buildup, we always want to clean up that surface to make sure there's no contaminants on the surface, to eliminate any risk of contaminants affecting the adhesion, and also to recreate that roughness. Typically, we don't have to do as aggressive a blast, but we still have to make sure that we have the cleanliness and the roughness we require for the application. So I would say the answer is probably yes. We need to go through the same process of preparation in order to build up the thickness again on existing material.
Thank you. Next question about the rate and speed of application. How many square meters per hour per day on average? So
typically in oil and gas petrochemical situations, the surface is not straightforward. It's normally irregular, and you've got different upstands and tray supports, etc. in there. So the way we manage large applications is by having multiple guns operating in the vessel at the same time. So we've just done a project this month or last month where we were doing 400 odd square meters, and because of the way we were able to install the scaffolding in that column, we completed that within 20 shifts. So we did it in 9.5 days. So the two key things we need is we need access, and then we need ventilation. We can provide the ventilation because when you're doing the blasting and the spraying, you create a lot of dust. We bring that equipment with us if necessary, or if it's already available with the client, we can do that. But as long as we are continually cleaning the atmosphere so the guys can see what they're doing, as long as the ventilation is sufficient and we've got the access, we can do multiple guns at the same time. Typically, we'd work with the client looking at your critical path, looking at the time you had to do the vessel, and then coming up with a plan of how we would achieve that, utilizing our resources.
Thank you, Colin. A question from Kieran. In case any local repairs are required on HVTS on subsequent inspections, can we do weld buildup, or do we need your help?
Yeah, no, I mean, you can do weld buildup, but what you'll do is there's a couple of things. You'll damage the thermal spray that's immediately adjacent to where you're doing the welding, because the high temperatures will cause the thermal spray to be damaged. And secondly, you probably need to remove the thermal spray so that you don't get any contamination or dilution of your weld. Because the thermal spray alloys will obviously leach into your weld pool if you don't remove it. So typically what would happen is you'd need to do some mechanical removal of the thermal spray, either through aggressive grit blasting or grinding in the local area where you're going to do the weld buildup. You do the weld buildup. If you need to do post-weld heat treatment, whatever, do that. And then ideally, IGS come back in and reapply the thermal spray. But if you weld in the location where the thermal spray is applied, then you will damage the thermal spray in that area, in that local area.
Mm-hmm. And another question about our online inspection. Are there any temperature limitations?
I think the limitation is the coupling gel you can use for your probe to make good contact with the surface of the metal. So I know we've done temperatures up to, I think, 120, 130 degrees C. So it's having the right gel for those for creating the coupling point between the probe and the substrate at those temperatures. If it's higher than that, then it's quite possible that it's not something that we can do online. And in some situations, clients have actually called us in when they have a shutdown, for a different reason. We don't have to go in the vessel, but obviously the temperatures come down so we can do the external inspection, or they're able to moderate their process so that the temperature comes down so that we can do it. Depends on the situation. But yeah, there is a limit, obviously, temperature limit to that.
Mm-hmm. Thank you, Colin. A question about chemicals in the media. So for heat-stable salt content in DEA, what is your maximum limit recommendation?
Sounds like a process question that should be forwarded to our friends at Amine Experts. I think from our perspective, the alloys that we utilize are going to be resistant to the corrosive species in the process. So we are not concerned really about the percentage of heat stable salts. But obviously, as an operator, you need to be concerned about that because it's going to affect your process efficiency. So I would suggest speaking to a process expert on those requirements.
Our Amine experts?
Yeah.
We will direct the question to them. And another question from Katalin about the daily variations of H2S content in the lean DEA solution. Mm-hmm. Can that lead to corrosion process in the unit?
It can, absolutely. And again, that's an operating parameter. What we would say is that if you have a robust corrosion barrier on your substrate, that will help protect you against that corrosion taking place. Where that takes place can be dependent upon, the location. Sometimes it's in the top of the regenerator, in the pipe work, etc. In those areas, obviously, we can't install a thermal spray barrier, so you'd need to use a corrosion-resistant alloy, perhaps, for that pipe work. But in the areas where you have the corrosion-resistant alloy installed, then you're going to be protected against corrosion. But absolutely, if you've got high variability and you're not managing that in your process, then that's going to lead to potentially to corrosion problems. I mean, again, there are ways to manage that in the process. You can dope with different materials. You can try to control that H2S content before it gets to the column. Again, that's a good question for our friends at Amine Experts.
So next question is from Julio. Any experience with reactive materials such as titanium, tantalum, or zirconium?
We have some experience with titanium. We have utilized historically titanium-based materials. The others, I don't believe so. I'm sure the metallurgists in our labs would love to get hold of them. I would need to ask a question, but I guess the question from me would be, what environment is it that you require those materials? Is it an environment where we can apply thermal spray? If it is, then we'd obviously be interested in having a look to see if there is some alloys that we could create that would work in that environment. So my knowledge at the moment is that we've used titanium historically, but the others, no, I don't believe so.
Okay. Next question from Johan. Is thermal spray cladding an economic alternative for new columns that are normally built with stainless steel, roll or overlay weld cladding? And can you compare the costs of a spray coating cladding with stainless steel 304L roll or weld overlay cladding, for example, on a new Amine absorber column?
So IGS, we are a field application company. So the work we do is in situ brownfield during shutdowns. We typically don't get involved with greenfield projects. There's a number of reasons for that. One of the reasons is economical. If you have a facility where you can build the vessel, you can install the cladding, do all your heat treatment, ovens, etc., then it's more economical to do it that way than to bring in a team from IGS to apply a thermal spray cladding. Where we deliver significant value is in on-site applications. So discovery scope or changes in your process conditions, changes in your operating conditions that mean you're starting to get corrosion activity where it wasn't originally expected to be from design. So greenfield, we don't tend to be involved with, principally from an economical point of view. Brownfield is really where we can deliver significant value.
Thank you, Colin. Let's have a look. So next question from Jignesh. What shall we do when we would like to apply HVTS again for new equipment which requires post-weld heat treatment due to thickness?
I mean, if you need to do post-weld heat treatment, most situations, the client will do all of the mechanical work they need to do, like pressure testing or post-weld heat treatment, etc., prior to the installation of the internal corrosion barrier. And that would be similar with high-velocity thermal spray. Post-weld heat treatment probably wouldn't be an issue for us, but typically it's not something that is done after the application of the high-velocity thermal spray. Typically that work is completed before, and then the internal corrosion barrier is applied.
Thank you, Colin. More of a question common from Santosh. So this technology has been in the market for a decade or more, and it's not widely used. What is the reason?
There's not enough of us. I think that's a good question. I think like a lot of these technologies, a client has to build the trust, or we have to build the trust with the client that what we're delivering offers real return on investment and real value. And sometimes it takes time for that to happen. I mean, one of the challenges with oil and gas industry is that, your shutdowns and turnarounds is every 3, 4, 5 years. So there is a certain amount of time needed to build that confidence. We also do a lot of work in the power sector. In the power sector, you're shutting down your boiler every year typically, or every 6 months. And so it's a much quicker and faster return, if you like, and a building of trust. So I think there's certainly a lot of potential. One of the reasons for doing this webinar is to hopefully reach out to more people, to make them aware of what we can do and the success we've had so far. And obviously we hope to do more.
Yeah, and I guess it's a case of information sharing, because it is widely used in some facilities and for some major operators.
Yeah, I think for operators who utilize it successfully, it is also, in reality, it's a strategic advantage for them, because it means that they are operating, effectively more efficiently. They're able to reduce their costs and produce more. So they're perhaps not that keen to tell all of their competitors about their successes. Okay. Well, once again, thank you all very much for joining us. We appreciate it, particularly given the current environment. So please, everybody, keep safe, keep your families safe, and we will hopefully speak to you again soon, or see you soon, preferably. So take care, and goodbye.
Yes, thank you all, and thank you very much, Colin. And everybody have a nice day.
Thank you.